MBA 633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll continue our discussion of hypothesis testing, and we'll see the mechanics of doing hypothesis testing with the population mean, but this time the population standard deviation is unknown. So we have an unknown sigma. The problem setting is the following. According to a 1995 demographic report, the average US household spent $90 a day. Due to the poor economy in recent years, the suspicion is that the average daily expenditure has gone down. And we want to confirm whether that suspicion is true or not. In order to do that, we took a sample of 30 households in Huntsville and obtained a sample mean of $84.5 and a sample standard deviation of $14.50. At the 5% level, what is your conclusion? So first of all, the 5% level that is given to you is the level of significance, meaning I'm willing to tolerate a 5% chance of making a type 1 error, calling the null hypothesis as false when in fact it's true, rejecting the null when in fact it's true. So I'm willing to accept a 5% risk of chance of making that mistake. So first step in hypothesis testing, set up the null and alternate hypothesis, the claim and the counterclaim. Recall what we said earlier, that the way we would like to set up the hypothesis is in such a way that whatever confirmation that we are seeking should be the result of a rejection, because we know we are minimizing for type 1 error, we are controlling for type 1 error. Therefore, when we end up rejecting the null hypothesis, we are fairly certain that there is a low likelihood of our having made a mistake. So we would like to structure the hypothesis in such a way that whatever confirmation it is that we are seeking should be the result of a rejection. Now, what is it that we're trying to establish here? We have a suspicion that the average daily expenditure has gone down. So let me set that up, mu less than 90. So I suspect that the average household expenditure has gone below $90. So I set it up as the alternate, because it would be nice if that confirmation were the result of a rejection of the null. Okay, so once I set up the alternate, mu is less than $90, then of course the only thing that's left for the null is mu greater than or equal to 90, because remember, when you put the null and the alternate together, those two claim and counterclaims together must account for all possible values of the population parameter in question, which is the mean. So we have our claim and counterclaim in place. The next step, of course, would be to go see what our sample tells us. And what our sample is telling us is that the sample mean is $84.50. The standard deviation, sample standard deviation, is $14.50. You can see we don't know the population standard deviation. So when we don't know the population standard deviation, you have recalled from our discussion during confidence interval that the sample mean has a t distribution, because we substituted the sample standard deviation in place of a known population standard deviation. We have introduced more uncertainty. So the sampling distribution ends up being a little fatter. So recall that all hypothesis testing starts with the assumption that the null is true as an equality. So what would the world look like if the null were true as an equality? If that was the case, then the sample mean, of course, would have the sampling distribution of the sample mean, that is, would have a mean of $90. Okay, and the standard deviation of the sample mean would be s divided by square root of n, which would be $14.50. $14.50 divided by square root of 30. That is what the standard deviation of the sample mean would be. And what are we observing in the sample? We are observing in the sample a sample mean of $84.50. So the sample statistic seems to suggest that the population mean has in fact gone below 90. But the question is it far enough below 90 so that it's highly unlikely to have occurred by chance? So by now you know how to figure out whether a value is particularly extreme or not, and we have to standardize things and all of that. But for this problem, we are going to use an alternate method of determining whether a sample statistic is extreme enough, and that is the critical value method. Critical value method. Okay, so in the previous problem that we worked, we used the p-value method. This is the critical value method. What the critical value method says is start from your level of significance. How much risk of a type 1 error are you willing to assume? I'm willing to assume a 5% chance of making the wrong call in terms of a type 1 error. So what am I saying? I'm saying that for this particular hypothesis, the claim and the counterclaim that we have, I'm willing to accept a value as extreme. I'm willing to accept a value as extreme provided the area to the left is 5%. This is a left-sided test, you can see, because the alternate hypothesis is mu less than 90. So I'm willing to accept any value as extreme as long as it is to the left of this critical value. Okay, so how do I get the critical value? The critical value is a point on the x-axis such that the area to the left of it is 5%. And how would I get that? You know by now that you would use an inverse function. This is a t distribution. So the t inverse function I would use, and because of the way Excel works with its t inverse function, I have to give it the area of two tails. So I want 5% to the left of the critical value. So the input that I have to give is t inverse of 10% because it wants two tails. And in our case, the degrees of freedom would have to be put in also, which is sample size minus 1. So which is 29. Okay, so let's see what this gives us. Equal to t inverse of 0.10, 29 degrees of freedom, and that ends up being 1.7. Okay, so I know that my t critical is equal to minus 1.7. So what we are saying is I will consider any value of the sample statistic to be critical enough if it is more than 1.7 standard deviation to the left of the mean. So this is my threshold. So let's see what my sample statistic ends up being once it's normalized. So this is the test statistic. Test statistic is simply the sample statistic normalized for our comparison purposes. So the value that I got is $84.50. How extreme is it? So for $84.50 minus the presumed mean of $90, that's what the mean of the sample distribution would be if the null were true as an equality, divided by the sampling distribution's standard deviation, okay, which is $14.5 divided by square root of 30. So that's what the sample tells us, and let's see what value we get. I'm running out of real estate here, so let me do the calculation over here. So I have 84.50 minus 90, which is the numerator, and the denominator is equal to 14.50 divided by square root of 30. Okay, so I divide one by the other, and I get a value of minus 2.07. Minus 2.07. Now notice when I compare these two, okay, So should I conclude that my sample statistic is very extreme or not? Based on the level of uncertainty I'm willing to accept, the likelihood of making the wrong call, I'm willing to accept a 5% chance of making the wrong call. That translates to a critical value of minus 1.7, meaning any sample statistic that is less than 1.7 standard deviation below the mean, I will consider it highly unlikely to have occurred by chance, and then I would reject the null. So what do I actually find? I actually find from the sample that the sample mean of $84.5 when standardized ends up being minus 2.07. So it's 2.07 standard deviations below the mean. So it's obviously crossed beyond the threshold. So the comparison tells us that T, the test statistic, is less than the critical value. Why am I doing a less than comparison? Because the alternate hypothesis is a less than. So because T is less than T critical, I end up rejecting the null. Okay, so that is the conclusion of this analysis, this hypothesis test analysis. So you would go back to whoever did this analysis and say, hey, the sampling data that we have seems to support your suspicion that the average daily expenditure rate has gone down. Of course, subject to that assumption that there is still a small probability that we made a mistake, but it's highly unlikely if I'm willing to accept a 5% chance of making a mistake, of making the wrong call, that is saying that the null is false when in fact is true. If I'm willing to accept a 5% chance of making that mistake, then I'm in good shape here. I would say that reject the null. So I would reject the null and end up saying that the average daily expenditure has gone down. Now, what if I were only willing to accept a 1% chance of making the wrong call, making a type 1 error? Then, of course, my critical value would be something else altogether. So my critical value would be T inverse of 0.02, because now the left side area is no longer 5%, it's 1%. Okay, so I put in a T inverse of 0.02 since it needs two tails. I still have 29 degrees of freedom. So I end up with a value, a critical value of 2.46, which is what I would expect. If I want to be more sure, if I'm only willing to accept a 1% chance of making a type 1 error, then what this threshold of 2.46 is telling us is that I will consider a sample statistic to be really extreme if it is more than 2.46 standard deviations below the mean. But our test statistic is minus 2.07. It is not, in fact, more than 2.46 standard deviations below the mean. So if I set a threshold of 1% likelihood of making a type 1 error, my conclusion would be there is not enough evidence to reject the null. So at the 1% level of significance, I would be unable to confirm the suspicion that the average daily expenditure has gone down, but I would be able to confirm that suspicion at the 5% level of significance.